Hello there. So recently I've been developing my problem a little bit better and understanding some important concepts in machine learning. So I looked into this and found for learning machine that finds parameters of fuzzy system, which fuzzy sets is an important concept in um, biology learning for neural networks and is a key aspect in neural psychology. And so it uses set theory, and you can see in the second paragraph there, classical set theory, the membership of elements in a set assessed in binary systems. So for ones and zeros, and basically what I was trying to do was use one of my, I guess, theories or hypotheses for one of the blindsight tests I did for myself with throwing a ping pong ball against a wall. So for a predicate, which is a mathematical or a logic symbol that it has a that represents a property or relationship, a relation with semantics and or of logic. Predicates are interpreted as relations. And for predicates in different systems, you can see I went down here to show that set theory, which I was using for trigonometry in R three-dimensional space, can be used in fuzzy logic. And predicates are the characteristic functions of a probability distribution. So log normal is what I'm going to get in one of the clips a little bit later. And I went to Fuzzy Neural Networks, a survey, which I can't download because in the video here, I just highlighted and I said recently in a survey, learning about algorithms and applications of fuzzy neural networks. It says for regression, fuzzy systems, and more. I went down there and just went up, down, trying to find a DOI. I saw the DOI a little bit later and clicked on it, but it just brought me back to academia. So I use academia primarily for some things. I think you can, I think some are free, but also for Google Scholar, which I'm using on this. There were some, you can see academia there. There's also archive or ARXIV, and while that wasn't listed, it's fine. So I just went back to the normal Google, went to finite element method or FEM models, FEM, which sounds hilarious for the common mind. Finite elements, so finite element method, which I was using for time dependent systems. I was looking through some of these characteristics, and it says discretization, which is a discrete system. An application, which I just went into highlighting here for complexity of both learning models and analysis of a system. And analysis of a system is very important when I'm using it in the sense of throwing a ball and mapping where it goes, blindsight in the space. And I looked down here for more fields and was just looking around finite element machine, finite volume method, so multiphysics, multilinear. And I have some papers here that I was going through. I also showed Big O notation, which is a classification of, or for algorithms with, to show how their runtime works, which is important in analytic number theory. I went into infinitesimal asymptotics, which I was using for the logarithms, which in most of these examples you can see logarithms or logarithmic action. See down there properties, 9 log n, and characteristics of exponential function, a complex plane. So this problem of an inverse relationship like 4 log squared of 4 to the 28 is a complex relationship. So for natural logarithms, which I'm using in this example, which is just log of x, or with a denotion of e, and you could use natural logarithms don't use base 2, I don't think, as a person getting into more of these fields. So I believe there is a distribution that can be mapped with these images or plots. I believe there is a plot that you can use for the probability of log normal distribution. So new logarithmic operational laws so I'm going back to this. Logarithmic operational laws, lol. Pythagorean, which is in R3, or like our observable space where matter collapses into three-dimensional space, utilized for solving decision-making problems, which again, relating back to neural psychology, shows that there is a relationship between logarithmic probability density function, because I'm using densities and logarithms to denote the relation between several different fields, which I've been working on as of recently, including my circular system of gradient density, or density gradients, and log normal distribution, a continuous probability distribution of a random variable in which a logarithm is normally distributed. I showed for this and went to the Wikipedia page, clicked on that, log normal, and went to applications, I believe, for this. Definitions, generalizations, and parameters. You can see E, or Euler's number, approximates the density. I do believe is a correct application. In human behaviors, I tried to find something, went to this, which it did not give a available PDF. I just decided to go to the DOI because it makes sense. I couldn't get this, I don't think. Proposed geometric measures of accuracy and precision, which again, for this application I was using in the neuropsychology of testing the relation between the logarithmic distribution and tangent on a flat plane for the wall and how it bounces. So again, as a preliminary, going back to logarithm, and that's where it goes. So to explain a little bit better at the end of this video, right now I'm going to say how this relates. So if I have 28 or 27 throws, there's going to be a probability of 4 that without seeing the ball, because naturally you're going to open your eyes and see the ball and catch it, if you have a muscle memory to open your eyes and catch the ball, then you're going to catch the ball with your eyes open, and that counts as a false. So when you catch it, there has to be a certain probability you can determine, and in this deterministic way, I decided to show that a number of throws denotes the inverse relationship of how many perfect catches or near perfect absolute catches, and a tangent of that off the wall is very coincidentally equal to the small variation, which tangent of 4 is 0.6. When I go back to the calculation, also coincidentally, of 4 log squared of 4 to the 28, it is only approximately equal to 28, because when you see the approximation, you can probably subtract the tangent. I believe so. Not quite sure about that. I'm still trying to figure out how. It is late and I'm ready for dinner. But to explain just a little bit better, in the calculation using for log squared of 28, it comes out to 4.06 repeated decimal to infinity. So that shows very interestingly that there's a relation. Okay, there's a relation between the tangent on the flat plane, which is where you hit the ball however many times, and you can also use auditory inputs to map your understanding. So back into the video, there's just a bunch of interesting factors that came out to the conclusion that this inverse relationship of throws and catches is very, very, very interesting in trigonometry and logarithms and time-dependent systems. and fuzzy neural network systems. So this is a informal proof for that work.